check it works.
Okay.
Okay.
Are we set?
Yes.
Okay, please. Matan Ben Dov from Bar-Ilan.
Yeah.
Please.
Hi. Hello, everyone. My name is Matan Ben Dov. I present our work about quantum state encoding using parameterized circuits. This work was done with the guidance of my supervisor, Emanuele, Torre, and with collaboration with Makmal. And also David Schneider, who's done part of the work, is also here, so you can ask him about the experimental parts. And okay, so let's start. So my goal here in this work is pretty simple. I try to find a circuit that encodes a given state. So for example, if you give me a quantum state, I want to be able to translate these different amplitudes or different description of the quantum state. I want to be able to prepare the state on a quantum machine, on a real quantum computer, using 2-qubit gates. So for the scope of this work, I'll only talk about pure state. And basically, I can talk about two versions of this problem. Either I'm given a classical representation of the state. It can be either a list of amplitudes of the state or some other classical representation, explicit representation. I want to be able to prepare it, to encode it on a quantum computer. This is very useful for various quantum algorithms. For example, for simulating quantum dynamics on real quantum hardware, you may want to start from a specific state, non-trivial state that you want to start from, or for quantum machine learning that you want to encode classical data onto a real state and do some variational algorithms with. And another version of this algorithm is if I'm given, instead of a classical description of the state, I'm given a quantum state encoded already inside the quantum computer, and I want to recreate a sequence of gates that will produce the same state. So here I'm I assume that I have as many copies as I want, and another version is useful for different kind of algorithms. For example, for circuit recompilation, if I want to read the same state by fewer steps, or for quantum state tomography, I want to probe some properties of this state, I may use this algorithm. So I'll present both of those, if I have enough time, I'll present both of those versions and compare between them. So first of all, about classical representation. So I'm given, so this is, to reiterate, this is very useful, for example, for quantum machine learning. For example, you can see here a general diagram of how hybrid classical, quantum classical algorithms are done in classical machine learning usually, and the first part is this state preparation. I want to be able to encode my state. Okay, so in order to do that, so I can do like the basic algorithms, I can just take all my amplitudes and decode them using some known algorithms, which basically they decompose my state bit by bit into a 2-qubit gate operations. But this is very hard. This may take an exponential number of gates. So I want, instead of doing that, I want to find an approximate solution. So I want to find a solution that uses a low number of gates, low number of layers, and to get a result which may not be very accurate, but still will get me a very good result. And to do that, I may want to look at a specific family of states which has relatively low entanglement, because if the state has high entanglement, I don't have much of good chances to encode it, even approximately using a shallow circuit. It will be very hard. So in order to talk about a family of low entanglement states, I'll start with an MPS. So I want to thank Maxime for presenting here what matrix product state is, so I can shorten this part. So here I have a matrix product state is basically a description of a state that I can control the correlation, the amount of correlation between the different number of qubits. So here here I present it as a diagram, as a tensor diagram. Each qubit is represented by a physical index, and the state or the correlation between the state is transferred through a bond dimension. And I can control the amount of correlation between the qubits by the bond dimension, the maximal dimension of the indices that goes between the different qubits. Also, you can also think of it as the dimension, the maximal dimension of all of those matrices. And using this description, I can use this description in order to translate. So it's pretty easy to translate using this description the MPS into a sequence of gates that will encode our state. The only problem here is that they will be a very large gate usually. So if chi is larger than 2, these gates will be 3-qubit gates, 4-qubit gates, which are very, very hard to implement by themselves. So I still end up with a very deep circuit that is very hard to implement. So how do we proceed? So a previous method suggested in the literature was to try to build our circuit a layer by layer. So using the fact that if I have chi equals 2, I can directly transform my state into one layer of 2-qubit gates and to entangle directly my MPS, I can do it step by step, take my matrix product state, truncate it, and transform it to the first layer, and then truncate apply the first layer, truncate the state again, and find the next layer. So I won't go here into details specifically, but it's pretty. But the main idea of this method that you find the layer one by one. You each time find the next layer that brings you closer and closer to have closer and closer approximation of the target state. And the problem with this method is that it's not efficient. It may be decreed like the infidelity. So this is the infidelity, the lower the better. If it's 0, I succeed. And for different circuit steps, so if you add more and more layers, the infidelity decreases, but not very efficiently. You can see you can either have 4 layers or 8, 9 layers, and you won't detect any difference for encoding. In this case, it's a ground state of Ising Hamiltonian. Okay, and so we wanted to improve on that, and to do that, we wanted to use optimization. So basically, here we use classical optimization, and we optimize a tensor network. We optimize a tensor network that starts with our state psi, and each gate tries to decode, decode the state bit by bit until it reaches to 0. So what we do is we stick to the same structure of the circuit given by the previous layer by layer method, and we optimize it further. And this optimization can be done using different methods. So the most simple, you can do it using gradient descent, each time calculate the gradient and taking a step. Or we did it by a slightly different optimization scheme, which is taken from the world of quantum of tensor network optimization. And it goes like that. We fix all the gate and we pick one gate, and we ask ourselves, what is the best gate that we could put here that will maximize our fidelity? And apparently this question is pretty easy to answer. It has an analytical solution. So we just calculate the gradient, and from this gradient according to a matrix, we can obtain the new gate, the optimal gate that we can put here and improve and get maximal improvement of our fidelity. So this is just a linear algebra. Okay, you can also describe it using tensor diagrams. But when we do that, we just have to, we found this optimal gate, and we have to move to the next gate. And we do the same. We find the optimal gate, the next gate, and we sweep over all the gates again and again, and we converge, actually. So you can see here like the infidelity as a function of number of iterations, and you can see that the infidelity drops quite considerably. So we started from the run initialization. This is 0 iteration, and when we start, the first iteration improves upon the previous method, and you can see that we more or less converge. And okay, so this is the first, the previous result, and we improve it. So, and here you can see what's the result for different number of layers. So the more layers we have to, so the first thing to notice is the first line is the previous method Bar-Ilan. So this is the layer by layer, this is the result of the layer by layer solution. And after the optimization, you can see that we can have an advantage of 1 or 2 order of magnitudes for certain types of matrix product states, and some other improvements as much as we can for random MPS. And you can see that the more layers we have, the more like we have to put in more iterations in order to see an advantage. For example, if we want to use the 6 layer instead of 3, we'll have to use more. Okay, we have to use more iterations in order to see the benefit of using more layers. And I won't go into that, but we also did the experiments on real quantum hardware. For an example, we choose an example of an MPS, and we wanted to demonstrate that this difference in the two encoding schemes can be noticed on real quantum hardware. So on IonQ, we got an access to more accurate machine, and we got a noticeable difference in the fidelity of the encoded state. Okay, so now I'll just briefly talk about the optimization of quantum hardware. So in this case, everything, like we still do the optimization. The only difference here is that the optimization is done on the quantum circuit itself. So we don't simulate quantum networks. We just calculate the gradient and go and do our optimization scheme using the gradient that is evaluated from the circuits on the quantum computer. And now the optimization scheme changed a bit. Now the question is, how can we retrieve this fidelity according to a gate? So we can either use a parameter shift rule or an alternative method that we developed, gradient tomography, that we kind of we do kind of tomography choosing different Pauli matrices in order to measure different parts of this tensor. And using this optimization, we can still get good results. The only problem is the scaling. So if you look at how the gradient magnitude scales as a function of the number of qubits, you can see that it exponentially decreases. This is known as the barren plateau problem, vanishing gradients. The more qubits you have, basically your Hilbert space becomes enormous, and then you can't really measure the direction of the gradient. This is problematic, and we had, especially when on quantum machines where you have noise threshold of shock noise, that we can't really, so from one point we can't really go, we can't really measure any gradient. And to mitigate that, we checked 2 different methods. Either we start near the optimal point and we just try to walk the extra step to improve our results, so to use good initialization, or to use local cost function, which basically compare the local properties of our encoded state as the target state, instead of just comparing, just calculate the overall fidelity, which is inherently global in terms of qubits. And I don't have time, but we saw that initialization still, like it improves the decay rate, but the decay is still exponential. But when we switch to local construction, then the scaling becomes polynomial, and we can scale our algorithm up to as much qubits as we need. And you can also see that the optimization, the algorithm, the optimization converges for local optimization. And with that, I will finish here. And thank you for listening. And,